Okay, so our next oscillator we're going to look at, as far as how it can be set up. Now, reading the notes, you should be able to see that this could be set up as a bistable multi-vibrator, A-stable multi-vibrator. It can be set up as a monostable, or it can be set up as a one-shot. In this example, we're going to look at some of the basic functions of the 5/5 timer and how it's going to be used as an oscillator. Okay, so there are some things to discuss within the 5/5 timer. So let's again, it's a 5/5. So what we're looking at here is the chip, right, with all the associated pins. Again, there's the notch indicating the front of it, and then you can, counterclockwise around to the final. A couple of things to note is that we often put ground. A ground needs to be placed on pin 1, and power, or VCC, needs to be placed on pin 8. And if you're not looking to reset the flip-flop, you need to provide power on pin 4, and I'll just explain that in a second. And we'll talk about setting a pin 5 is used for changing the reference voltage to another one. So I'll get into this in a second. So let's talk about some of the main components that happens inside, or what's going on inside the 5 timer. So for all intents and purposes, what we have is two comparator circuits. Okay, so we have comparator CA right here and comparator CB. Okay, so you can see here from the voltage going to pin 8 all the way to pin 1 tied to ground, what we have is just a voltage divider. Notice the resistance values are all the same. So it's easy to say that the voltage value at this point will be roughly 2/3 the voltage, and at this point would be a quarter of the voltage, right? a third of the voltage, not a quarter. So this would hold, this resistor, since they're all the same, would hold a third of the voltage, and at this point would hold 2/3 of the voltage. Okay, so that sets these reference voltages. Notice that these are flipped around. What we have here is the reference voltage is set on the non-inverted, and the reference voltage is set on the inverted side. That's going to play an important role. Next, these outputs for each of these comparators just goes to a set-reset flip-flop. Notice that the output of the flip-flop is the inverted. Okay, it's the inverted output. That's for good reason. Then, so that's just our flip-flop. Then it goes to an inverter to go out. This output gets tied to, we'll talk about this guy in a minute, but gets tied more importantly to this Q1. Notice that, let's just treat Q1 as a switch. If the output, or Q0, goes high, the Q1 will basically, because it's just a NPN, will basically turn on and short pin 7 to ground. Okay, that's an important concept to understand right now. Okay, let's just imagine this for a second, that let's go through the cycle here. Now, notice that we have resistors here and here. Okay, so I'm going to just pick a state. So the first state I'm going to pick is the fact that Q0 is low. Okay, I'm just going to say that this point is low. So let's start with this point. We'll say this point is low. Right, just put a 0 there. The low doesn't turn him on, so we have no ground at pin 7. Okay, so for all intents and purposes, notice that we have VCC, we have RA, RB, and this capacitor tied to ground, right? This little portion of the circuit going through here, right? Going through here. There's that little portion of the circuit. So if there's no ground here, we have a straight shot from VCC to that capacitor, and we have two resistors in between. The combination of the resistors and the capacitor set up the RC time constant. So basically at this point, with no ground here, basically this capacitor is charging. Okay, so it's charging. So when it gets to a potential, now remember we have reference voltages set here and here. So when it gets to a potential that it becomes large enough, because it's across pin 6, it sets the potential for pin 6. So at some point, right, at some point pin 6 is going to be high, and notice that this ties to pin 2 on this side. So at some point pin 6 and pin 2 are both going to be high. Okay, so we're going to put a 1 here and a 1 here. Now, again, it's voltage potential we're talking. We're going to assume that these potentials set the flip-flop as such. Okay, as in like this, if it's a 1 here, it's going to be greater than the reference. And if there's a 1 here, it's going to be greater than the reference. So with these conditions, this sets this output low, right, because that's the inverted, and it sets this output high. Now, this is the reset, this is the set. If reset goes high in a standard, remember that this is a standard set reset flip-flop, where if it's in its normal inactive state, right, nothing changes. But now we set reset high, which also sets Q naught high. Okay, so now another thing to note is when we were low here, we actually had a high output. Okay, that output went high because we have an inverter here. Okay, so now we change things. What happens is the inverter output goes high. This activates this line, right? Because we went high. We turn this switch on, tying a ground at this point. If we tie a ground at that point, what essentially we've done is the power now just goes straight here to ground, and that capacitor is just left to discharge. And it discharges across pin 6. And eventually we get to a point where that high that was there is now considered a low when we consider it against the reference voltage. Okay? When considered against that reference goes low, which means this goes low. Now we're low. If we're low here, we're also low here. Because remember, they're connected across, right? So because you can basically say that this point and this point is the same point. So if this point went low, which put a low here, this point also went low. So what this does is it sets the positive output. So now set goes high, and this goes low, which puts this as a low, like there. So what we have is our output, because this is the invert, goes back to low. And the low, what the low does is it removes the ground when it goes low. It puts our output, right? Because remember, when we were 1 here, our output went low. So what we'd be seeing on the output here is initially when we're at the 0, we would have saw a square wave, and it would have been something looking like that. We're talking digital circuits, right? So what we have here, it would have went, when it was low, it would have went high, and that's this riding this wave now. And then when it went high, because it's an inverter, it went low, which is just what happened. Okay? So now we're back at the, we're back going low here, right? Which means that going through the inverter, we're going back high over a certain period of time. So we've gone low, we removed the ground on pin 7, which means that capacitor is allowed to charge up. It charges up again, and it gets to a point where it's considered high, and then the cycle just continues. And what we have as a result of this is a free-running oscillator providing us with a repetitive wave, right? And the width of these pulses totally depends on the charge and discharge time constant of that capacitor, how it's setting these 2 points as highs and lows. Okay, so what we have essentially is a free-running oscillator. Now, this Q2 at this point is very important, because if he's not, so this is a, first let's look at this as a PNP, and we have a reference voltage here. So by putting VCC here, we basically ensure that the reference voltage is not put there. So it doesn't play a role, nothing's going on here. By tying this point to ground, right? So if we took the VCC off and tied that to ground, what we would do is we'd activate this Q2, which would then set the reference voltage here, forcing the output low. But basically what this does is it disables the output to force it low. So if you put pin 4 to low, your output would start to just get stuck low. Okay? And for all intents and purposes, as it works, that's how it works as an oscillator. Now, pin 5 is, you'd use pin 5 if you wanted to change this reference voltage to something other than set by even values, you see. So you can see that you're limited on the 5-5 timer because this exactly has to be 2/3 of whatever VCC. If you wanted to change that for whatever reason, you would put another potential here, which would offset it, right? You can change it to whatever you want at that point. And that's the 5-5 timer as an oscillator.